Today we're talking about how Fable solved the Jacobian conjecture. We previously did a video around what the Jacobian conjecture was, but today we're going to talk more about how it was actually solved. Here's a tweet that disproved the conjecture, and let's get into it. So to start off with a definition. For a polynomial map between two complex spaces of n dimensions, if the determinant is a non-zero constant, the map should be invertible. So that means each input should correspond to one output and vice versa. Let's visualize this to make it a bit clearer. So this graph shows three different inputs and their polynomial maps applied to them, and they all end up in the same output. And this is what the conjecture said isn't allowed to happen. If you want to understand the conjecture itself, it's better to take a look at my last video, but now let's get into how this was disproven. So to properly understand this, there's a few areas of maths that you should know. So I've split this video up into the following 7 sections. The way we solve this really is to create a polynomial map between different bags of numbers in projective space, which chapter 1 and 2 covers, and then in chapter 3 we essentially perform surgery on these projective spaces to make sure the transformation has a non-zero determinant. And then in chapter 4 we do some more surgery to convert these projective spaces to complex spaces by removing hyperplanes. But the surgery leaves some rugged edges, and we show how it's possible to clean these up in chapters 5 and 6, before finishing on chapter 7, where we show how Terence Tao did the algebra to clean it up properly, which leads us to Fable's solution. So that might sound quite complicated, but it should make more sense at the end. But let's start off with explaining what the projective space is. So first of all, let's take an x and y dimension and plot a bunch of lines on there. Each line carries a specific gradient. So each of these lines represents a ratio between two real numbers, and each possible ratio maps to one of these lines. So for example, the coordinates 2 and 4, 6 and 12, and 20 and 40 are all a ratio of 2, and they'll all be represented by the line with the gradient m equals 2. So when the line goes straight up, the gradient becomes infinite. And since these lines represent all the ratios, we can actually do something clever here. So if we draw a semicircle over the lines, we can now represent each ratio with an angle. So let's show how this works. If you pick an angle between 0 and pi, it will correspond to a point on the edge of this semicircle, which in turn corresponds to one of these lines. So each of these lines is a single point of the projective line P1. So yeah, as the angle approaches pi over 2, the gradient tends towards infinity, as you can see here. But this is the way that each of the angles corresponds to each of the gradients. So if we wanted to plot the relationship between the angle that we pick and the gradient that we get, we'd end up with a graph like this. So you can see here it starts off moving up slowly, and then as we approach pi over 2, it shoots off to infinity, and then once it comes past the other side, it comes back like this. So an interesting fact about this graph is this is actually the graph of tan. But yeah, so let's move on. So those projective lines represented a ratio between two real numbers. But how can we represent a ratio between two complex numbers? So let's plot a complex plane with a real and imaginary axis, and on this plane we have a and b, which are two complex numbers, and a third complex number m, which is the gradient of the ratio between a and b. So you can see here how m changes as we vary a and b, and m is a point of the complex projective line. So m2 can have a gradient of infinity. So how are we going to represent that? I'll show you. So that was kind of a weird thing we did there, but basically if you zoom out and you take the edges of the complex plane as they expand to infinity, you can kind of like morph them up, fold them up, and pin them together at the top with the point of infinity like this to create what's called a Riemann sphere. And what this does is it gives a valid point on the graph to place m when it has a value of infinity. So that's the difference really between the projective space and the complex plane. So you can see here how a value in the projective space maps to a value in the complex plane. It's pretty much the same at first, but then as you zoom out and the number gets further and further away and closer to infinity, it ends up with a place to reach infinity in the projective space, whereas there is no such place on the complex plane. Now let's get into bags of numbers. So let's take a bag of 3 numbers, 2, 3 and 5. We can create a polynomial whose roots land at these points like this, and then when we expand the equation out, the coefficients follow the Eters formulas. So the first coefficient for x cubed will always be 1. The second coefficient for x squared will total the negative sum of all the numbers. The third coefficient for x will be the sum of the pairs of the numbers, so 2 times 3 times plus 2 times 5 plus 3 times 5. And the fourth coefficient, the constant, will be the negative product of all the numbers. So the interesting property that emerges here is that no matter how you order the bag of the 3 input numbers, the output equation will always be the same. So this creates a system that allows you to convert a bag of 3 unordered numbers into 3 coefficients that have an order to them. So let's try this again, this time with complex numbers from the projective space instead of real numbers. So the same logic applies. A bag of 3 unordered numbers from the projective space corresponds to 3 coefficients that have an order to them. So we first find the polynomial equation with these roots, expand it out, and we get these coefficients. So this idea of converting between a bag of 3 unordered points to a bag of 3 ordered points. And this idea generalizes as well. So let's expand on that. So this is sim notation. So sim n notation means n amount of unordered points. So you could take sim 1 unordered points from the P1 projective space, find a corresponding polynomial that has those roots, and then get a corresponding ratio between the 2 coefficients. And this ratio would correspond to 1 point in the P1 space, as you can see here. You could take a sim 2 unordered points from the P1 projective space and find the corresponding polynomial that has those roots. That'll be the quadratic there, ax squared plus bx plus c, and then get a corresponding ratio between the 3 coefficients. And this ratio will correspond to 1 point in P2 space. And then sim 3 we've already shown. This was a cubic in our original example. So you could do this for any value of n. Take sim n unordered points from the P1 projective space, find a corresponding polynomial that has those roots, and then get a corresponding ratio between the n plus 1 coefficients. And this ratio will correspond to 1 point in Pn space. So this is explaining how we go from P1 space to P3 space. So in each of those instances, you could normalize it so the ratio equaled 1, leaving the rest of the coefficients as a bag of n ordered numbers. So let's look at a particular transformation where the source space has a bag of 2 numbers and the bag of 1 number. So we'll call the bag of 2 numbers Q and R, and the separate singular number bag as a marked point P. So then we apply a pi transformation to these bags, and it merges them into one singular bag of 3 numbers, which sits in the target space. So this output corresponds to a point in P3 space, the space where it measures 4 coefficient ratios. So if you looked at the bag after the transformation in P3 space, you wouldn't know which point was originally separate. There'd be 3 possible pre-images, and there's no way for you to tell which one has the actual pre-image. A could have been the marked point, or B could have, or C could have. So let's plug in some examples here. If A is 1, B is 2 and C is 3, this is what happens to it, let's see. So first of all, we want to express this basically in forms that we can do algebra with. So to do that, we need to find the polynomial for the bag of 2, and then take those coefficients and we can label them as S1 and S2. And then the marked point P just goes in as it is because it's a single point. So we'll pair up the marked point P and the points S1 and S2. There we go. So this gives us these coordinates in the source space. So a quick note about the source space is that the point in the source space can be written geometrically as two bags as it is on the left, or in the coordinates as it is to the right after we change it to the S1 and the S2 values. It's both the same point in the source space, but it's just two different representations of it. But this source space is P1 for the marked point multiplied by sim2 P1, so the group of 2 points. And when we multiply the two polynomials together, we get a cubic equation with the following coefficients. So this is what happens when you combine the two bags into one singular bag, and this is the pi transformation. So this is the pi transformation P plus S1, PS1 plus S2, and PS2, one for each of the coordinates and how each of the coordinates are transformed. So when we plug in these coordinates, we get 6, 11, 6 for the top one, we get 6, 11, 6 for the middle one, and we get 6, 11, 6 for the bottom one. So take a second to note that the source space before the transformation is P1 times sim2 P1, so that's one dimension plus two dimensions, and then the target space is P3, and that's 3 dimensions. So that's a transformation with 3 dimensions in and 3 dimensions out, where multiple inputs map to the same output. So this is exactly the right shape that we need, except it's currently in the projective space instead of in the complex space. So let's take a look at the determinants to see if they're non-zero as well. So the pi transformation equation is quite simple, and it's expressed here. Let's get that up. There we go. So what we need to do is find the Jacobian of this equation, and we can do that by finding the partial derivatives of each of the coordinates. So the first coordinates function P plus S1, the derivative in respect to P is 1, the derivative in respect to S1 is just 1, and the derivative in respect to S2 is 0. So that's the top row of the Jacobian. And then we can do the same calculation to the other two functions to fill in the full Jacobian. And then once we have the Jacobian complete, we can do some linear algebra to find the formula for the determinant there. So we get that as P squared minus PS1 plus S2. So we can plug in each of these coordinates to see what the determinant is at each of these pre-images. So if we look at that for each of the ones there, we get 2, minus 1, and 2. So none of the determinants here equal 0, so that's good. So let's recap on what we've learned here. We have a source space, P1 multiplied by sim2 P1. That's a 3-dimensional source space. A pi transformation is applied to it, and we get 3 inputs arriving at the same output in the target space, which is P3, also a 3-dimensional space. The determinants at each of these example points are non-zero, so we're getting relatively close to disproving the Jacobian conjecture. There's still a couple of things to do though. So the first thing we need to do is convert the projective spaces here into complex spaces, and the second is to make sure the determinant is actually non-zero everywhere, not just at these 3 points. So next up, let's get into the ramification divisor. We previously derived the formula for the determinant, which is P squared minus PS1 plus S2. So this is expressed in terms of the coordinates from the source space. But if we factorize this and express it in terms of the bags from the source space, we get this. The determinant is P minus Q multiplied by P minus R, where P is the marked point and Q and R are the grouped points. So if we set this equation equal to 0, this tells us where this transformation has a determinant of 0. So this happens whenever the marked point is equal to Q or R, any of the points in the group. So we need to resolve this. To disprove the conjecture, our transformation needs to have a constant non-zero determinant everywhere. But there is obviously a space there where the determinant is 0. So we call this the ramification divisor, and this is the set of numbers where the determinant is 0. So there you go, when P equals Q or when P equals R, and all the possible variations where that might happen are all contained within the ramification divisor. And what we need to do is express this source space as the source space with the ramification divisor cut out of it. So we essentially need to perform surgery on this source space to remove that ramification divisor of R. And now, for every possible pi transformation that can be applied to each of the values in the source space, the determinant will be non-zero anymore, because any point that would have been zero has been removed by definition. So this might feel like cheating, but we haven't dodged the problem, we've just traded it for a different one. The question is now whether what's left is still a genuine three-dimensional complex space. So we have a polynomial map pi that maps three different inputs to the same output, with non-zero determinant everywhere, and this map is not invertible, so we are close to disproving the Jacobian conjecture here. There's only two problems left. The target is projective space, and we need it to be complex space, and the source is a product of projective spaces with a surface cut out of it, which is even further from complex space. So to disprove it, we need to figure out how to convert both of these spaces into the complex space. Now let's get on to the hyperplane. So let's start off with the target space. To disprove the conjecture, we need to transform the three-dimensional projective space P3 into a three-dimensional complex space C3. So you can see there, that's when the point approaches infinity. And so what we need to do is just slice off that point by removing the hyperplane. And now none of the points can reach infinity once we remove the hyperplane, as you can see here. So to understand what the hyperplane is, let's consider the projective space P1, where each space represents a ratio, or each point on the space represents a ratio between two numbers Z1 and Z2. So let's say you impose a condition on this space, the Z2 must equal 0. As we go around the points in the sphere, we see that most places don't have any possible value of Z1 that's valid. The only time that there is a valid value of Z1 is when that projective point is at infinity, at which point every value of Z1 is valid. So this is the infinity point on the projective line. So if we define the point where Z2 equals 0 as H, we can simply remove that, and then if we remove that set from the projective space, that just leaves behind the complex plane. So this explains the hyperplane to P1 space, but what about P2 and P3 space? So let's start with P2, and the point on P2 is a ratio between 3 points and can be represented as a line going through the origin. So if you imposed a Z1 equals 0 condition on this P2 space, similar to P1 space, the only directions in the space where a valid Z2 and Z3 could exist is at a gradient of infinity. And in the P2 space, infinity no longer lies in a singular point, but as a line. This is the only way there is any valid Z2 and Z3 value, is if the gradient is infinity here. So, to visualize this better, let's imagine that you're in an ocean. As you look into the horizon, you first see 1 meter ahead, then 10 meters, then 100 meters, then a kilometer, then 10 kilometers, and as you look into the horizon, you approach infinity. And if you do a 360-degree turn, this infinity line wraps entirely around you. There are all these different directions that you could travel to approach infinity. Of course, this is an analogy, using a real space to picture to represent a complex space is it can never be perfect, so bear that in mind, but this is just going to give you the idea. So let's say now that you define the hyperplane H as the points in P2 space where Z1 equals 0, you can simply remove that from P2 space and you'll get C2, a two-dimensional complex space. So you're removing any possible values of infinity. So we're doing more surgery there. So then let's step it up to P3, the three-dimensional projective space. Again, we just set this up a dimension. It's no longer a line but a plane, so to remove this plane where z1 equals 0 from P3 space would leave C3 space. So of course, to remove this set from the target space, you'd also need to restrict the source space, so no point on there maps to the now removed set of H. So the source space must not contain the pi inverse of H. So to recap, we now have two three-dimensional spaces where a polynomial map is not inversible. There's three input maps. There's three inputs mapped to the same output. The determinant is non-zero throughout all of it. The target space is C3, and the last piece of the puzzle now is the source space. So we now need to make the source space the points of P1 multiplied by sim2 P1 space that survive both restrictions of R and pi minus 1H to be a three-dimensional complex space as well. And once we've done that, we'll have disproven the Jacobian conjecture. So to try and achieve this, we can tune the hyperplane, which we'll go into in the next chapter. How do we tune the hyperplane? So to explain this, we first need to understand what a Mobius transform is. So if we take a look at the P1 space, one point in projective space, each point represents a ratio between two complex numbers z1 and z2. So we can pick four coefficients a, b, c and d, and then transform the z1 coordinate to be az1 plus bz2, and then transform the z2 coordinate to be cz1 plus dz2. And with those degrees of freedom, we can change those two numbers in any way we want, and thus change the ratio between them and where they lie in the P space. So this works for every possible point in the P1 space. So you can see here, as we select different values for the four coefficients, the Mobius transforms can change the shape of the P space in pretty much any way. By setting the B and C values to 1, we convert the gradient of each point to its inverse, and in doing so we flip around the infinity point and the 0 point in P space. So this shows that even the point of infinity is not fixed in this space. So previously we had been discussing the hyperplane being removed when z1 was set equals to 0, but the key thing is we can actually set the hyperplane to any equation. For example, if we define the hyperplane as a set when z1 equals 2z2, for example, here we go, it moves the hyperplane point that's being removed, and that goes to a different point in P1 space. But we can just do a Mobius transformation with the coefficients, so we can also map the infinity point onto the hyperplane that was removed. And this is continuing theme. No matter what equation we use to define the hyperplane, we can always do some Mobius transformation that maps the infinity point onto that hyperplane. So this means that no matter what equation we set, removing the hyperplane can always be combined with the Mobius transform. And that removes infinity from the space. And thus any hyperplane removed from projective space will convert it to complex space. So that's in P1 space, but if we look at P2 space, the same logic applies. We can define the hyperplane in any way, and then define the P2 equivalent of a Mobius transformation. This is called a projective transformation, in a way that will map the infinity points to that hyperplane. So no matter what hyperplane we pick, we can always just map the infinity points there. And in P3 space, we can do the same thing. Let's show that in a second. So yeah, we get a plane this time, and we define the hyperplane via any equation, and then set the projective transformation to map the infinity plane onto this hyperplane that we will be removing. So now we've shown that the way we tune the hyperplane is by adjusting the equation that defines the set, and no matter what the equation that is, we can always trust that we can rejig the space so infinity is removed with the hyperplane. But then that leads to the question, if the removal of infinity isn't changing as we tune the hyperplane, then what is changing? So we'll answer that in chapter 6. So let's take a look at what happens to P3 space under projective transformations. So the point can move anywhere, but there's still a defining feature. If all 3 points begin with the same value, they will all end on the same value as well. So we can visualize this by creating a curve in the space where each of the 3 points are the same. So if the values P1, P2 and P3 are all equal, no matter what projective transformation occurs, they will end up at another point on the curve. This curve is preserved by every symmetry of the space, and it's an invariant structure within it that we'll call I. So now let's take a look at the hyperplane within the target space. So here's a fact. No matter what equation we use to define the hyperplane, it must meet this invariant curve I at exactly 3 points. It has 3 roots. So to explain this, every point that can exist in the curve is a bag of PPP values. So if we write the polynomial that has roots at these values out, let's take a look at what equation we get. So this is the equation that we get out of it. When we expand it out, we get the ratio of ordered coefficients as 1 minus 3p, 3p squared and minus p cubed. And the hyperplane is defined by some function of a0 z0 plus a1 z1 plus a2 z2 plus a3 z3 equals 0. So where the a's are the specified coefficients for that definition of the hyperplane, and the z's are the ratios representing that point in P3 space. So let's plug in the formula for the ratios of the points that land on the invariant structure I into the hyperplane set H, and we get a new formula that expresses which points P of the curve I are in the set H. So there we go. This equation has 3 roots, and that is where the point P is equal to the value of R1, R2 or R3. So to make any one of the brackets equal to 0, and that's the entire equation. So these values depend entirely on the coefficients that we choose for the hyperplane. So if we change, as we change the hyperplane, these R1 values, the point where the roots are, changes. So as you can see here, as we change it, you can see the hyperplane changing around. And if we watch what happens as we tune the hyperplane, you can see that R1, R2 and R3 continuously change, but the specific values wherever they end up are not permanent, as a projective transform could move them anyway. What is permanent about this is if all the ratios, if all the roots are at the same place, or even if a couple of them are at the same place. That feature is preserved no matter what projective transform is applied. So the continuous values are changeable by the projective transforms, but what isn't changeable is the discrete answer to the following question. How many of the roots are distinct? So here we see 2 of the same root and 1 separate. You saw before 3 of the same root. And we can describe this as 3 different categories. So if all 3 roots are distinct, the equation is crossing. If 2 of the roots are combined and there's a third singular root, that equation is tangential. And if all 3 of the roots are combined, that equation is osculating. So these are the 3 discrete options, and these are immutable features based on the tuning of our hyperplane. So the next question is, so what? So the reason we are tuning the hyperplane in the first place is because we're looking for something called a special case. So to give you an intuition for what a special case is, let's take a look at this toy model. So we have an x and y axis with the equation of t equals xy, and if we set t to 6, this is the resulting graph. You can see that you can set x to a specific value and use the formula to find the corresponding y value by giving 6 over x. You can notice that if you try and set x to 0, there's no corresponding y value because you can't divide by 0, so y doesn't have a valid corresponding point there. So this holds true for almost every possible value of t. There's never a valid y when x equals 0, and that is everywhere apart from at one point, and that's when you set t equal to 0. So you can see when you set t equal to 0, since x multiplied by y is 0, that means that if x is 0, the y can be any value, and the same with y. If y is 0, x can be any value. And so this is a special case. You can see how this is a special case here. So every ordinary slice of this family is missing the point at x equals 0, but one special slice comes along where all those missing points finally exist. A family of slices, all alike and all incomplete, and one special slice that behaves completely different. So let's compare how this is to the way that our system behaves. So if we look at the source space and consider, we have a marked point P and a bag of 2 points Q and R. So let's set P to a specific value and look at how R and Q may vary at this slice of P. So we have the ramification divisor R, which, as we explained earlier, is the set of numbers where Q equals P or R equals P, and the determinant hits 0 for a specific slice of P. This should just look like a cross. As long as one of the values of R or Q is equal to the slice of P that we take, this point will lie within the set R. So as we move around the values of P, it ends up shifting the cross. So this is what it looks like at different slices. Now let's take a look at the inverse hyperplane. So if we take a specific hyperplane example, for example z2 equals 0, how does this map to this RQ axis at a slice of P? Well, if z2 equals 0, that means the coefficient of x, which following Vetter's formulas is the sum of the pairs, also equals 0. So PQ plus QR plus PR equals 0. So we can express this as Q plus P multiplied by R plus P equals P squared, and then rearrange to express R in terms of P and Q. So R equals P squared. Let's see. P squared divided by Q plus P minus P. So let's plug in some real numbers here and start at the slice here. Let's see. We see that it creates this hyperbola. And it's much like the toy model, that if you want to find R when Q is equal to negative P, there's no valid solution, which is true for all cases except when P equals 0. And at this point, you can see here, R can be any value as long as Q is 0, and Q can be any value as long as R is 0. So this point is a special case where both sets that are due to be removed coincide exactly. So as we change to different hyperplane equations, this logic holds true, except the merge occurs at different values of P. So if we change it from z2 equals 0 to a different function like this, we still get this special crossing point of both R and pi minus 1h. It just changes to a different position. So if we look at the three discrete options that we have, let's take a look at this in a second. Showing more examples there about how they always work. So yeah, this is the so this hyperplane equation is the one that's taken at the crossing type. So as I said, there's three discrete sort of equations the hyperplane can exist in. So it can be either crossing, tangential, or osculating. So if it's crossing, that means it's got three distinct roots, and the merge point, the special point in these equations, just looks like this, where the corner just brushes across the cross, so it doesn't really merge. We don't have that same effect as we do when we have a doubled root, and we've already shown you what happens when there's a doubled root. So let's take a look at what happens when you've got a tripled root and it's osculating. So osculating has a special case that is too big. So if the entire plane at p equals 0, it's unusable because it's taken away more possible input values than even the crossing equations have. So you can see there the different discrete options of the hyperplane and the corresponding special cases for each of the options. So yeah, the tangential shows a case emerge when the two sets due to be removed are exactly the same, and this is the special case that Terence Tao uses to explain how the disproof actually works, which leads us to the final chapter. So Terence Tao contributed to this problem by using algebra to look at the problem in a different way. So how can we map C3 to this source space that has two pieces, pi minus 1 h and r, cut out of it? Tao's solution was to first make the equation L and the equation Q that represented the marked point P and the grouped bag Q and R respectively. As you can see here, L had coefficients A and B, and Q had coefficients C, D and E, and LQ gave the polynomial equation for the combined bag of the three unordered points. So let's show you that. So when LQ is expressed in terms of the A, B, C, D and E coefficients of the L and the Q, we get this. ACX cubed plus AD plus BC x squared plus AE plus BD x plus BE. So when expressed as a ratio, the equivalent values of Z0, Z1, Z2 and Z3 are AC, AD plus BC, AE plus BD and BE. So can you recognise what we're doing here? Let's see, so if we take a look at a lower dimensional representation of this ratio, so this is just a ratio in P3 space, but let's take a look at a lower dimensional representation of it. So it just ends up as a point in P space like this, and each line through the origin is one ratio, and every point along it is the same ratio written at a different scale, if you remember from chapter 1. So now imagine that we impose the condition that Z1 must equal 1, you get this blue line here. So every single ratio would be represented on this line. Every single line crosses it exactly once, and that, well, every single line except when Z1 equals 0, which is the gradient being represented at infinity there. So in our real case, there isn't just one orphan line, there's a whole hyperplane's worth of directions that miss the slice, but the mechanism is still the same. So if we specify that of this LQ equation, we only want to look at the slice where Z1 is equal to 0, we end up looking at a space that has the hyperplane removed. So no points at infinity exist within this space. And this can be achieved by imposing the equation AD plus BC equals 1, since AD plus BC is Z1. And now Z1 is pinned to 1, we have three free complex numbers, which is Z0, Z2 and Z3. And this is our three-dimensional complex space. So imposing that Z1 equals 1 is a tangential case as well, with doubled roots. So we could have imposed that Z0 equals 1, but that would have been an osculating case, or even a crossing equation. But any option that isn't tangential falls apart later on, so we need to make sure it's tangential. So then we have one more imposition to do. So since LQ is a combination of L and Q, 2L times by half Q will have the same output as L times Q. And the coefficients could be scaled to 2A, 2B, half C, half D, half E. And that's an extra degree of freedom that we don't want. We don't want to deal with that, because this scaling factor could be any amount, and we'll call this variable lambda. So we need to add another imposition to ensure that we only take the set for one value of lambda. So to do this, we use a tool called a resultant between L and Q. So to summarise, a resultant has two properties. It's 0 exactly when L and Q share a root, and it's when we scale the pair of equations, L and Q, by lambda, the resultant scales by exactly the same amount. So to find it, we first find the root of L, which is negative b over a, and then we plug that root into Q, and then we multiply through by a square to clear the fraction. There we go. And that expression is a resultant. So check the algebra yourself and you'll see it works out. And so by setting this value to 1, which we do here. That's a second imposition, and we're picking out one value of lambda where this happens, and disregarding every other possible scaling, and that keeps the degree of freedom pinned. Furthermore, the resultant equation equals 0 when L and Q share a root. So if you remember the ramification divisor R that we removed from the source space to ensure the determinant was non-zero, that was the set of any values in which L and Q shared a root, and the marked point P is equal to one of the byte points Q and R. So by setting the resultant to any non-zero value, we're also excluding any other points that could have been on the ramification divisor. So it's doing two jobs in one there. So to recap, we have these two impositions, and we're looking at the slice of the possible projective space of the function LQ, where AD plus BC equals 1, to remove the hyperplane and the degree of freedom, and the subslice of that, where the resultant equals 1, to remove the ramification divisor and add another degree of freedom to make sure the determinant's not 0 when we remove the ramification divisor. So this gives us a coefficient space of AC 1, AE plus BD, BE, which is 3 free complex numbers, degrees of freedom, so it's a C3 space. So that means we now have 5 values, A, B, C, D, and E, that map to 3 values, AC, AE plus BD, BE. So we can express, you can see how as we change the 5 inputs there, those 3 outputs change. But we can express D in terms of B, C and A, and we can express E in terms of B, C and A as well. So I'll show you that. So there's D in terms of B, C and A, and there's E in terms of B, C and A. So this only works when A doesn't equal 0 because we're dividing by A, so otherwise that would be impossible. So as long as A doesn't equal 0, we now have 3 complex numbers, A, B and C, that map to 5 complex numbers, A, B, C, D and E, who in turn map to the 3 target coefficients of the LQ equation. So what about when A does equal 0? Well, first of all, let's show you what this looks like. So you can see here we have 3 free coordinates that determine where the 5 other coordinates are. So yeah, let's now look at what happens when A does equal 0 to finish this off. So at this point, in position 1 would collapse to BC equals 1, and in position 2 would collapse to B squared C equals 1. So therefore we can derive B must equal 1, and so must C. And so when A equals 0, B equals 1 and C equals 1, and that's fixed. That only leaves the 2 free coordinates D and E. And this collapsing of variables, pinning of B and C, when A equals 0, only happens in the tangential case. And that's why the hyperplane we picked couldn't be crossing or osculating. It works because of the way the 2 cuts R and the hyperplane shadow land exactly on top of each other in one slice, like we showed in the previous chapter. And this is why Terence Tao had to pick a tangential equation. So this means that if we look at every value of A that isn't 0, we have A, B and C to map to all the possible A, B, C, D, E points. And then if we look at the value of when A does equal 0, B and C are pinned to 1, so it's just D and E that do the mapping instead. So different coordinates in each case, but the same shape either way. A 2-dimensional slice at every single value of A. So if you stack those along the A line, you get a 3-dimensional complex space, which is the exact shape that we've been looking for. So now all we have to do is normalize this so we aren't using separate variables. So if we do some algebra, we can express B, C, D and E in terms of the variables A, Y and Z. So therefore we now have, after this algebra here, A, Y and Z as the 3 C3 coordinates that map to the A, B, C, D, E. So let's take a look at the full flow. A, Y, Z map to A, B, C, D, E, which maps to all the possible source space equations. With no ramification divisor or hyperplane, and then that pi transforms to the target space. So that gives us a C3 space that maps to a C3 space, and there's a non-zero determinant everywhere, and we can choose 3 different coordinates as inputs, and they'll all map to the same output, so it's not reversible, and this disproves the Jacobian conjecture. you can see here, the three different inputs going in as A, Y, and Z. They go to A, B, C, D, E, and then to the source space and get transformed to the target space. So it's a big transformation, but yeah, we end up like that. So we can express that algebraically, where G1, G2, and G3 are the three polynomials that make up the map, and the Jacobian determinant of the whole thing is non-zero constant, so we can prove that. And the coordinates are three inputs, which map to the same output. So this can be normalized to the equations that Algebraic wrote in his tweet. So if we do that some factor there, we end up getting this, and this is exactly what he wrote in the tweet. So that's exactly how the Jacobian conjecture can be disproven. So thanks for watching this video, guys, and I'll see you in the next one.